Up in the north where I live, snowstorms can be so brutal that they can take down entire power grids, leaving thousands without electricity. But this issue of power grids being taken offline is applicable to anywhere where extreme weather conditions, such as hurricanes, earthquakes, and tsunamis occur. When these emergencies happen, it's natural to want to call for help, but if your phone is almost dead and your portable battery charger is drained, and there isn't an outlet near you, what will you do? There are commercial products that store or create electricity for later use, such as foldable solar panels, gasoline power generators, and battery banks, but all of them have a time and a purpose. These approaches are not intended to be portable, versatile, multi-use solutions to charge electronics over a prolonged period of time. Here, I present the e-shake. It takes inspiration from the 1980s hand-powered flashlights and the idea that it takes mechanical energy of a human and converts it into electrical energy. It is intended to be an emergency tool used when there are no other reliable sources of electricity. Before I started to manufacture some of my electronics, I went onto Tinkercad and used their electronic simulation to see if my 6-phase arc rectifier layout would work. Then I built a prototype of the circuit on a breadboard and tested to see if it actually produced electricity by spinning a motor. When I hand spun the motor, I could get a peak output of 150 milliamps and 2.24 volts, which is a massive improvement from my 8th grade version of 0.2 milliamps. Now that I actually proved out that this design could work, now I'm moving on to my mechanical design of the e-shake. Before we talk about the most current design, let me show you the two major iterations before I got to this point. In the first design, it was entirely focused on the ergonomics of the handle and its size. However, as a result of how complex and large the case was, when I checked how long each half of the case would take to 3D print, each side took 12 hours, which is far too long for a rapid iteration. So in the next phase of the design, I focused on making free-form structures that would be modular and would sandwich the mechanisms in place. However, the structure was very pliable and would deform under stress. As a result, I decided to design a very robust system that could handle a lot of physical abuse but also be modular and quick to iterate. The current design turns reciprocal motion into rotational motion. It does this with a handle that is attached to a guide. The guide then follows a sinusoidal path, but since the guide is only allowed to move linearly, the centrifuge with the sinusoidal path is forced to rotate. The advantages to this system is that it does not change the direction of the motion of the centrifuge or the motor, which means that the system does not need to fight itself with each stroke, leading to a predictable and reliable design. Second, it has few moving parts, which reduces the complexity and the total number of failure points. It has a robust design that does not require precise manufacturing. However, the major issue with this current design is that it is a one-to-one system. What I mean by that is that for every time I push the handle down, the centrifuge only does half a spin. That means if I want to meet the required RPMs to make it so that my motor spins fast enough to create the voltages I need to attach a very high gear ratio in between the centrifuge and my motor. Currently, I am testing out my design and improving along the way. I'm also researching into other mechanical mechanisms, such as the ball screw linear guides, just to keep my avenues open. I really want to get this video out to you just to share my research, but more importantly, I want to get everybody's feedback and recommendations on how to improve and grow my project. Thank you for watching my video, and stay tuned.